In this lecture, we consider another method of analyzing AC circuits, and this analysis uses something called nodal analysis. And this would be a situation where we have more than one AC source in the circuit, specifically current sources, and we can use this method to figure out what the voltage is across the nodes. So nodal analysis for AC is very similar to DC, where we just had resistors in the circuit. And so basically we can apply those same steps, and we have to use Ohm's law for AC, where everything is in terms of phasors. And we will apply Kirchhoff's current law at each of the nodes. So let's talk about the steps that we would follow. So the first thing is that we would want to make sure that all of our sources are current sources in the circuit, and if we have a voltage source, then we would need to convert it to a current source. So we notice in this particular circuit that we do have a voltage supply that's connected in series to an inductor that has a reactance of 2 ohms. So we can convert that combination of a voltage supply with some impedance in series into a current source in parallel with an impedance. The next thing is to label the voltage at each of the nodes and also to pick a ground. And that's already been done for us. So we have a node 1 labeled, node 2, and node 3, and then we also have the ground labeled here. Next, we would label the current through each of the different components, and after we label the currents, we'll write down the current through each of those components in terms of the voltage and the impedance. So we'll use the equivalent of Ohm's law, V equals I times the impedance, and we will write down what the current is. And then after we do that, we'll apply Kirchhoff's current law at each of the nodes, and then if we need to, we'll solve simultaneous equations where our unknowns here would be to actually solve for the voltage supplies, not the current. That's a misprint there. So we'll solve simultaneous equations for the voltage. All right, so the very first thing we need to do is to convert the voltage source to a current source, and in this case we can write down the impedance of this capacitor as the reactance of the capacitor, which is 2 ohms, and since it is a capacitor, it has a phase angle of -90. Once I know that impedance, I can replace this equivalent voltage source with an equivalent current source with a current in parallel with that same impedance value. The current direction would have to be in line with the polarity of the voltage supply, so it's pointing down. And the value for the current is just the voltage over the impedance. We know the voltage is 2 volts, phase angle of 0, and the impedance is 2 ohms, phase angle of -90. So that gives us a current of 1 amp with a phase angle of 90 degrees. And so we can take that circuit that had a voltage supply in it and replace it with this current in parallel with our impedance value. So the next step is to label the current in each of the different components, and you'll notice that before we do that, I went ahead and for each of the nodes, I color-coded them. And basically where node 1 is located, I just highlighted along the wire until I hit a particular component. And that means that every place where the yellow is located is node 1. And then I did the same thing for node 2. It's in green, but I went around and basically labeled until I hit a component. And then I have node 3 over here on this side. So my next step is to label the current in each of the different components. And so we'll start here with the inductor, which has a reactance of 2 ohms. I've labeled the current direction down, and then I've put the polarity in as the positive to negative because the current goes through that component from the positive to the negative, or it's a drop. I also labeled the negative side the ground, and the positive side is connected to the voltage V1. So after I write down, or after I describe the current direction, I can also define the current in terms of the node voltages and the impedance. So according to the equivalent of Ohm's law for AC, the current would be the voltage over the impedance. So the voltage across this particular component is V1, and the impedance is 2 ohms, phase angle of 90 because it's an inductor. As I make my way across, I have a current IB, which is going through another inductor, It's connected on one side to node 2 and on the other side to the ground. So again, there's the polarity that I've labeled. And the current is the voltage of the node, V2 minus 0 of the ground, over the impedance, which is 2 ohms, phase angle of 90. Then I get to the next component, which is a resistor, and again it's connected on one side to node 2 and on the other side to the ground. So the voltage is just V2, and then I divide by the impedance, and it is a resistor with 1 ohm resistance, and then it would have a phase angle of 0. I make my way over to my equivalent parallel impedance, and it has a value of 2 ohms with a phase angle of minus 90 because it was a capacitor. And so that current is going to be, the voltage on one side is connected to V3, and on the other side it's connected to the ground. So this is going to be V3 over the impedance of 2 ohms, phase angle of minus 90. At the very top, I have a capacitor that has a reactance of 2 ohms. I've labeled my current direction to the right, which means I would label my polarity positive to negative as indicated. That means that the voltage across this capacitor is going to be V1 minus V2, the difference between those two sides. And then I can find the current, which would be the difference in the voltage over the impedance, which is 2 ohms, phase angle of minus 90 because it's a capacitor. And then I get to the last resistor that I have in my circuit. I've labeled that current direction to the right, and so again plus to minus in the direction of the current, and so the positive side is connected to V2, the negative side is V3, so the voltage across there is V2 minus V3. And according to the equivalent of Ohm's law, it would be the voltage difference between the two sides over the impedance, which is 2 ohms, and this has a phase angle of 0 because it's a resistor. So I've labeled all of the current directions, and I have written down all of the currents in terms of the voltage across the component and the impedance value of that particular component. The next step is to apply Kirchhoff's current law at each of the nodes. So I go to the first node here, and I look at the sum of the current entering, and this has to equal the sum of the current that's exiting. So as I look at this node, I realize that the current that's entering here is I2. That's going into the node, and then coming out of the node is I1, IA, and IE. And so I've written those down here. After I use Kirchhoff's current law, I can plug in the values that I know. So I know the current I2 is 2 amps, phase angle of 90. I know the current through the 2 ohm inductor here, I've written down as V1 over 2 ohms, phase angle of 90. I know the current I1 exiting is 1 amp, phase angle of 0, and then the current IE I have written down here, and I have plugged that value in. So now I need to try to write this expression where I've applied Kirchhoff's current law in a nicer form. So I start with that expression that I have, and the next thing I'm going to do is I'm going to try to write this and get rid of the fractions. So, and I'm going to rearrange some things. So I'm going to get the voltages on one side of the equation and everything else on the other. So this 1 amp phase angle of 0, I've moved to the other side. And then for each of these terms, I have divided this out. So I assume I have a 1 here at the top. So I can write this first term as 0.5 phase angle of minus 90. So this is like 1 over 2 is 0.5, and the phase angle is 0, so 0 minus 90 is negative 90. And then I separated these two terms out, and I did the same thing. So 1 over 2 is 0.5, and then phase angle of 0 minus a minus 90 becomes a positive 90. And for the same reason, this term would look exactly the same, but there's a minus sign here. So now I'm going to collect like terms, and I'm going to try to add terms together. So I want to combine the two terms on the left, and then I want to combine the voltages as I can. So in order to combine the two terms on the left, I need to write them in rectangular form. So I've done that here. And in order to combine the V1s in both of these cases, I also need to write those in rectangular form. So I've done that also with V2. One of the things I notice is when I write these in rectangular form, that the two values that have V1 actually have the same term in them, and so they will cancel each other out. And so I have only one unknown in my expression, and that is the voltage V2, and I can solve for that. So I'm going to take the term on the left and I'm going to put it into polar form, and I'm going to do the same thing for the component here that's multiplied by V2. I've taken this minus sign and I've multiplied it through here, and that's why this is a negative 90. So I've got an expression, I have these phasors, I can now solve for V2, dividing both sides by 0.5, phase angle of minus 90. And I end up with 4.48 volts with an angle of 206.6 degrees. Now, this actually would be okay to use, but typically we want to use our angles between positive 180 and negative 180, so it's usually a good idea to convert this. And so if I convert 206.6 degrees, it's actually the same thing as negative 153.4. So if you think about this, this is in the third quadrant, and all I've done is I've gone from the axis in the clockwise direction and found that same point, so it's negative 153.4. Things will probably just work out better if we use angles between negative 180, positive 180. All right, so we have figured out what the voltage at node 2 was, and we got lucky because we thought we were going to have to solve simultaneous equations for this because we had V1 and V2 as unknowns, but things canceled out nicely for us and we didn't have to worry about that. Okay, so now going back to the same picture that we had before, we can look at node 2. So now we're going to look at this node, and we're going to look at the current entering and the current that's exiting. So as I look at my picture, I have a lot of current exiting. I only have one current entering. IE right here is entering that green node. Exiting is IF, I2, I3, IC, and IB. So basically everything else is exiting. So I can go ahead and I can plug in the values for these currents that I have listed over on the left. And so when I do that, I've got my IE here, my IF, I2, I3, IB, and IC. And so I've got a lot of terms here, right? So I've got unknown voltage V1, unknown voltage V2, unknown voltage V3. However, from the previous part of this problem, I actually solved for what the voltage V2 was, so I only really have two unknowns, V1 and V3. So let's try to reduce this. So starting with my expression that I have, I'm going to try to write this in a nicer form and combine terms. So the first thing I realize is that 2 amps 90 degrees, 2 amps 90 degrees can be written as 4 amps 90 degrees, and that's where this term is right here. So I've kept that on the right side of the equation, and then I have moved all the other terms, so V2 minus V3 over 2 ohms angle 0, and these two terms here I've moved to the other side of the equation. Not only have I done that, I've also divided by the bottom part of this fraction, right? So V1 minus V2 divided by 2 ohms phase angle of 90, 1 over 2 is 0.5, 0 minus 90 degrees is plus 90. My second term, when I move it to the other side, becomes negative. When I do the same thing here and I divide by 2, I get 0.5. 0 angle minus 0 gives me a 0. When I move this term to the other side, it becomes negative. 1 over 2 is 0.5. 0 minus 90 is a negative 90. And this side, moving to the other side, is negative. 1 over 1 is 1. 0 minus 0 is 0. So let's combine terms as much as we can, which means that we need to take all of these terms and we need to convert them into their rectangular form and factor out. So 0.590 is an imaginary piece multiplied by both terms, v1 and v2. 0.5 times 0 is just a real piece multiplied by v2 and v3 with the minus sign out front factored through. v2 times 0.5, negative 90 is a negative imaginary number. There's a minus sign out front and then there's a negative here. And then 1 times 0 is just a real number, so I just have a v2 here, and then I've got my term over on the right. So as I look at this, I realize that two of these terms, this term right here and this term right here, cancel each other out, so I can get rid of those. And I realize that the real part of the v2's actually add together, right? So I have a negative 0.5 and a negative 1, that gives me a negative 1.5. So if I combine all those terms together, I have an unknown voltage V1, I have an unknown voltage V3, I've got this V2 term, but I do know from the previous node that the voltage V2 is 4.48 with a phase angle of minus 153.4, so I can take that expression and I can plug it in for V2. So when I plug it in for V2, here we go right here, right? There's V2 multiplied by 1.5. I've also taken and I've put the V1 and V3 back into those terms back into polar form. And now I can multiply 1.5 times 4.48, 6.72, still the same phase angle of negative 153.4. I've got my V1 and my V3, which are my unknowns. I need to take this term and I need to move it to the other side. So I'm going to now add it to the other side of the expression. And I need to combine these two terms. They are currently in polar form and I need to add them, so I need to put them into rectangular form. So as I put them into rectangular form, I have an imaginary part for the first term, and then I have a real and an imaginary part for the second term. I can combine those together and I get a real part and an imaginary part. I can put this back into polar form and I get 6.08, phase angle of 170.5. And at this particular point, I realize that I don't know V1 and I don't know V3. So I may get to a point where I have to solve simultaneous equations. So I'm going to have to stop right there. But one thing I could do is I could solve for one variable in terms of the other, knowing that I may have to do some sort of substitution. So I can solve for the voltage V1 by dividing both sides by 0.5, phase angle of 90, and moving this voltage term to the other side of the equation, which makes it negative. And then if I divide out, I get 6.08 divided by 0.5 is 12.16. 170.5 minus 90 is 80.5. 0.5 divided by 0.5 is just a 1, and then 0 minus 90 is a negative 90. So I've at least written down what voltage 1 is in terms of voltage 3, and so now if I get another equation involving voltage 1 and 3, I can now combine those two equations and I can solve for the unknowns. But at this point we can't go any further. We're going to have to look at the next node. So now I'm going to look at node 3. So I'm over here at node 3 and I want to look at the current that's entering and the current that's exiting. And I realize IF and I3 are both entering this node right here that's blue, and then exiting I have I4 and ID. So I have IF plus I3 entering is equal to I4 plus ID. I can go back to my expressions over here for the currents and I can plug those values in. So IF, this current here, is just V2 minus V3. over the impedance, which is 2 ohms, phase angle of 0. I3 is 2 amps, phase angle of 90. I4 is 1 amp, phase angle of 90. And then exiting here, ID is the voltage V3 over 2 ohms, phase angle of minus 90. So now I need to try to rearrange this expression and solve. So as with what I did before, I'm going to get rid of the fraction. So if I divide by 2, because this is essentially just a real number 2, I get 0.5. So I have V2.5 minus V3.5 from the term here. I have, in terms of imaginary numbers, in the rectangular form, since it's a phase angle of 90, this would be 2 amps imaginary piece. This would be 1 amp, an imaginary piece, and then if I do the same thing here and I divide by 2, I get 0.5. 0 minus a minus 90 becomes a positive 90. So now I can rearrange terms and I can move things around. So I'm going to move the current 2 amps with the phase angle of 90 to the other side. I'm going to move the V3 over here, just rearranging things, and writing this this term here that for the voltage V3 in terms of rectangular form, this would be 0.5 with an imaginary piece, and then when I move it to the other side, it becomes negative. I remember that I already found out what the voltage V2 was from the first node, and so I can use that here and I can plug it in. And when I plug in that voltage V2, I have to multiply it by 0.5, and then I can also combine the two terms for the voltage V3. I have a real part that's 0.5 and I have an imaginary part that's 0.5. And then when I combine the two current pieces, I just have a negative 1J. When I multiply by 0.5, it gives me 2.24. When I move this term for the current to the other side of the equation, it becomes negative, right? So this term has been moved over here, and then the voltage V3 is moved over to the other side of the equation and it becomes positive. And I have also taken the rectangular form that's in front of V3 and converted it into the polar form. I need to add these two terms together, or subtract, I guess you would say. And in order to do that, my term here needs to be in rectangular form. So I convert that into rectangular form, and then I'm going to add it to the piece over here. Turns out that the two imaginary pieces cancel, and I'm just left with minus 2 volts equals V3, and then I have my, my polar form that's multiplied by V3. I can write negative 2 as 2 with a phase angle of 180, and now I can solve for V3 by dividing both sides by 0.707 with a phase angle of 45. 2 divided by 0.707 is 2.83. 180 degrees minus 45 is 135. So I have my voltage V2. I now have my voltage V3, and luckily I haven't really had to solve simultaneous equations. So the last step is to figure out what the voltage V1 is, and I can go back to my expression where I solved for V1 from node 2 in terms of V3, and I can plug in the value that I have for V3 here. When I plug that in, I can now multiply by my phase angle of minus 90. 135 minus 90 is 45, and then there was a 1 here, right? So this is still 2.83. I need to subtract these two quantities. They are currently in polar form. I need to put them in rectangular form. Once I have them in rectangular form, I can subtract, and it turns out that this 2 and this 2 actually cancel, and I'm left with just an imaginary piece, which means that my voltage V1 is 10 volts with a phase angle of 90 degrees. So it was a lot of work to get to this answer, but I had a pretty complicated picture that had capacitors, inductors, resistors. I kind of got lucky because in this example, a lot of the components had reactance or resistance values of 2 ohms, which made solving this a little bit easier in terms of not having to really solve simultaneous equations. But the steps that you would follow using nodal analysis are exactly what we did here. So we were able to find the voltage of the node at 1, the voltage 2 here, and also the voltage 3 on the third node. So this is just a guide on how you would set up any problem of this nature, and keep in mind that it's possible that you may have to solve simultaneous equations.